We want to begin our discussion on potential energy and conservative forces. The idea behind a conservative force is that the amount of work done by the force does not depend upon the path it takes in moving from one position to another. So for example, if I have an object which starts off at position R1 and it moves to some other position R2, then it might take a path, or we'll call this path 1, or it could take a direct route, we'll call that path 2, or some really strange route, which we'll call path 3. And no matter which of these paths the object takes in moving from R1 to R2, the work done in moving from 1 to 2, which is the integral of F, the net force, dotted with the displacement, dr. So we integrate from R1 to R2. This amount of work will be the same whether it takes path 1, path 2, or path 3. In mathematics, one way that we talk about this is to use what we call a closed integral. And you have learned or will learn about this in Calculus 3. The idea behind a closed integral is that I'm going to start at some position and I'm going to move along the path. Again, it shouldn't matter what path I take, and I end up back where I started from. In this scenario, the net work done on the object will be 0. So in this scenario, the integral of F dot dr, where F is the conservative force, that will be 0. There may be other forces acting on the object, but the force we're interested in, the conservative force, will yield a 0 work done. So let's consider an example. Let's consider a book on a table, and we're going to say the weight of the book is 1 pound. And what I'm going to do is I'm going to lift the book straight up a distance of 2 feet. Then the work done by gravity, U sub g, is equal to minus 1 pound, that's the force, times 2 feet, that's the displacement. Now the force is down, hence the minus sign. The displacement is up. And so I end up with minus 2 pound-feet. Then I'm going to move the book to the right, a distance of 3 feet. Now the work done in this scenario is equal to 0. Because the force is down and the displacement is to the right, the vector dot product, F dot dr, is equal to 0 because they're at 90 degrees to each other. Then I'm going to bring the book all the way down to the floor. And we're going to assume the floor is 3 feet below the table. So I'm falling a distance of 5 feet. So the work done by gravity in this part of the path is minus 1 pound times minus 5 feet. And so I get positive 5 pound-feet of work done by gravity. Then I'm going to move the book to the left, again a distance of 3 feet, but just like the last time, the force is down, the displacement is left, I'm at a 90-degree angle, so that's equal to 0. Finally, I bring the book back to the original position. So during this part of the path, I'm going up 3 feet. So I have minus 1 pound times a positive 3 feet, which is minus 3 pound-feet. And so what you're seeing, I've closed the loop now. That's what I mean by this closed path. I started off at this location. I ended up at that location. So that's a closed path. And the work done by gravity is minus 2 plus 5 minus 3, which is 0. So there's no work done by gravity in this path. Now this is a very specialized and easy path. The idea behind this is that no matter what path I take, I'm going to end up with 0 work done by gravity because it's a conservative force. Now what would not be a conservative force? Okay, a force that is not conservative would be friction. So let's take the same book on the same table, but now I'm looking at the top of the table. And we'll start off with the book at this location. 1 pound is the weight of the book. Let's assume the coefficient of kinetic friction is equal to 0.25. Nice simple situation. The book is flat on a level table, so the normal force is equal to 1 pound. Therefore, the frictional force, the kinetic frictional force, is equal to 2.25 pounds. So what I'm going to do is I'm going to move the book in this direction 4 feet. Now keep in mind the force due to friction is in this direction. Since I'm sliding it to the right, the force due to friction is to the left. So there's F kinetic. And so the work done by friction is equal to minus 0.25 pounds, because it's to the left, times 4 feet. And that's going to equal minus 1 pound-foot. Then I'm going to take the book, which is now here, and I'm going to move it this direction 2 feet to this location. So I'm pushing it down. I'm not worried about the work done by me. I'm only concerned with the work done by friction. The frictional force is in this direction. The displacement is in that direction. So for the second part of the path, it's minus 0.25 pounds exerted over 2 feet. The two forces are in opposite directions. The dot product is negative. I get minus 1/2 pound-feet. We'll move it back in this direction. That's 4 feet again. The frictional work is equal to minus 0.25 pounds. Actually, let me do it this way. Let me say plus. The work due to friction is plus 0.25 pounds because the force is to the right. The displacement is to the left, negative 4 feet. And I get negative 1 pound-feet. Finally, I'm going to move up. In that scenario, the frictional force is down, the displacement is up, and you can see I'm going to get minus 1/2 pound-feet, just like I did in this part of the path. When I add all these together, the total work done by friction is equal to minus 3 pound-feet. That's not equal to 0. Closed path. Right? So I started here, I go around this path, I end up there. Closed path, not 0. Friction is not a conservative force. How do we know if a force is conservative? Well, there's a couple of different tests. One, of course, you can do the integral. But another way of testing is to do what we call the curl of F. Some of you may have seen this before. But a curl involves the del operator. That's what this is right here. You may not have seen this. This is the del operator. And it's a differential operator, but notice it's also a vector. So the del operator is equal to the partial with respect to x in the I hat direction plus the partial with respect to y in the j hat direction plus the partial with respect to z in the k hat direction. That's exactly what the del operator is. F will be some force which may have a function value in the x, y, and z direction. And so this cross product, if I use determinant notation, this cross product is I, j, k, partial with respect to x, partial with respect to y, partial with respect to z. And then I put f sub x, which might be a function of x, y, or z, the y component of f, and the z component of f. And I evaluate this determinant. So we have to assume that f is going to be a vector function of x, y, and z. There is also a del operator in the polar coordinate system as well, and we'll look at that in just a minute. But if the curl of the force is equal to 0, then I have a conservative force. If I'm interested in what is the force, one way I can generate the force, if I know the potential energy function, again, V might be a function of x, y, and z, or in polar form, it could be a function of r, theta, and z, cylindrical coordinates. Then if I operate the del operator right on the scalar quantity, so notice I'm using a vector operator on a scalar quantity, that's going to give me a vector value, minus del v looks like this. This is a vector quantity, and it's an operator, so I'm taking the partial derivative of the potential energy with respect to x. I'm taking the partial derivative of the potential energy with respect to y and with respect to z, and I put those in their respective I, j, k vector, unit vector values. That's going to give me my force F. In polar form, it looks similar. Partial with respect to r, 1 over r, partial with respect to theta, and then partial with respect to z. So it's of a similar form except for this 1 over r, which keeps my units all nice and happy. Because notice I have partial with respect to a length, partial with respect to a dimensionless quantity, so I need a length down here in the denominator to make that work, partial with respect to a length again. So that's the polar form of the del operator.